Hello everyone, welcome back to ChemOrgChem. Today we are going to explore the Negishi cross-coupling reaction, a powerful method for making carbon-carbon bond formation. This reaction named after Ei-ichi Negishi, who was awarded the Nobel Prize in Chemistry for his work in this area. Let's dive right in. Before moving that, if you are new to this channel, don't forget to subscribe. So in this lecture, we will cover the fundamentals of Negishi coupling and its catalytic cycle and some key example to illustrate its applications. By the end of this video, you will have a solid understanding of how this reaction works and how it can be applied in synthetic organic chemistry. So here is the general scheme for the Negishi coupling reaction. So here you see an organic zinc reagent react with organohalide or organotriflate in the presence of either nickel or palladium catalysis to form the new carbon-carbon bond. So this reaction is known for its high selectivity and mild reaction conditions. So when you come to the ligand, mostly triphenyl phosphine is highly desirable for this type of reaction. Apart from triphenyl phosphine, you can use either achiral or chiral phosphine ligands also. You can use. And active catalyst for this reaction is either nickel 0 or palladium 0 complexes, but this can be generated in situ from the more stable nickel 2 or palladium 2 complexes. Next, moving on the catalytic cycle. First, we are going to see the nickel-based catalytic cycle. So now you see this nickel complex after the complexation with your ligand that form the nickel 2 complex. So this nickel 2 complex react with organozinc by transmetalation reaction to produce this corresponding nickel 2 complex. After that undergo reductive elimination to produce catalytically active nickel 0 species. So once you generate the nickel 0 species which readily undergo oxidative addition with either organotriflate or organohalide to produce this corresponding nickel 2 complex, which then readily undergo transmetalation with organozinc reagent. So here you see this R group just to transfer into the nickel metal. At the same time, X also transfer into the zinc to produce this corresponding byproduct along with this nickel 2 complex. So after that, which quickly undergo trans cis isomerization to produce this corresponding complex, which then readily undergo reductive elimination to produce this corresponding carbon-carbon coupling product. So next, moving on, another catalytic cycle which is based on the palladium. So initially you can take the palladium 0 or palladium 2 pre-catalyst. When you take the palladium 2 pre-catalyst, if you use some suitable ligand that will generate in situ palladium 0 or palladium L2, so this one is a 14 electron complex which readily undergo oxidative addition with organotriflate or organohalide to produce this 16 electron complex. So here you note that palladium oxidation state is 2, so which then undergo transmetallation reaction by the reaction of this complex with organozinc reagent. So just like our previous case, so this R group transferred into the palladium center, at the same time X also transferred into the zinc center, which produce this corresponding 16 electron palladium 2 complex, which then quickly isomerize, trans-cis isomerization takes place to produce this corresponding 16 electron complex, then which then undergo readily reductive elimination to produce this corresponding carbon-carbon coupling product. So apart from that, here you should note that, so when you use electron rich ligand that facilitates the oxidative addition that undergo faster, and similarly when you use some bulky ligand that facilitate reductive elimination should undergo faster. And in this catalytic cycle, transmetallation reaction usually a rate determining step. That means that this step is slowest step in the catalytic cycle, and especially when you take the carbon sp2 zinc transmetallation faster when compared to the carbon sp3 zinc, and sometimes people use lithium bromide, lithium chloride, zinc bromide additives in order to boost up the reaction. So where lithium salt presumably break up the aggregates to generate the monomeric zincate species which readily undergo transmetalation in order to undergo the further this isomerization and reductive elimination sequence to produce this corresponding carbon-carbon coupling products. The Negishi reaction is particularly important in the synthesis of natural products, pharmaceuticals, and advanced materials, and its ability to form carbon-carbon bond efficiently, which makes it a attractive toolbox of organic chemists. So before moving to the Negishi coupling reaction example, we should know how to prepare the organozinc reagent. So here you see these are the reagents we can use for Negishi cross-coupling reaction. Let's see how to prepare this class of organozinc compounds. So this is the one of the method. So when you take the organohalide, when you treat with n-butyl lithium, which readily generate this corresponding organolithium species, which then react with zinc bromide, which readily produce this corresponding organozinc compound. So this is the another method. When you take the organohalide, when you treat with zinc copper couple, which readily produce this corresponding organozinc reagent. So this is the another method. When you have some Grignard reagent, when you treat with zinc bromide or zinc chloride, which produce this corresponding organozinc species. So here you see this one is a vinyl magnesium bromide, which react with zinc bromide to produce this corresponding organozinc bromide species. This is the another method. When you take the organohalide with activated zinc in presence of diethyl ether, which readily produce this corresponding organozinc compound. And similarly, you can take the alkynyl bromide with activated zinc in the presence of diethyl ether, which also produce this corresponding organozinc compound. So apart from this is another general method. When you take the zinc chloride along with potassium, which readily undergo reduction reaction to produce this corresponding zinc 0 species, this one is called Rickey zinc. So which then react with various organohalide to produce this corresponding organozinc compound. So let's look at our first example. So here we are going to synthesize the bi-aryl compound using Negishi cross-coupling reaction. So according to this reaction, this organohalide, so here is your organochloride compound, which react with this organozinc compound in the presence of palladium catalysis to produce this bi-aryl compound. So next moving on, this one is another example. Here you see this iodo compound initially react with isopropyl magnesium bromide. So when you react with isopropyl magnesium bromide, which readily produce this corresponding Grignard reagent, which then react with zinc bromide, this one produce this corresponding organozinc species, which then react with iodobenzene in the presence of palladium catalysis to produce this corresponding carbon-carbon coupling product. So this is the another example. So now you see, so this bromo compound, which going to react with this 2-pyridyl lithium species. So this 2-pyridyl lithium species initially react with zinc chloride, which generate in situ corresponding organozinc species, which then react with this bromo compound in the presence of palladium catalysis to produce this carbon-carbon coupling product. So next moving on, some more example. So here you see this compound. So this compound, when you react with n-butyl lithium, which readily abstract this proton, since this proton is more acidic, therefore which readily abstract this proton to produce corresponding organolithium species, which then react with zinc chloride to produce this corresponding organozinc species, which then react with 2-bromopyridine to produce this corresponding carbon-carbon coupling product by using palladium catalysis. This is the another example. So up to now, we have seen the carbon sp2 and carbon sp2 coupling. So here we are going to see the carbon sp3 and carbon sp2 cross coupling reaction. So now you consider this example. So this iodo compound, when it react with zinc, which readily produce this corresponding organo zinc iodide species, which react with 2-bromopyridine in the presence of palladium catalysis, which produce this corresponding carbon-carbon coupling product. So this example demonstrates the versatility of this Negishi reaction. It forms the different types of carbon-carbon bonds. So next, moving on. So this one another example. So now you see this iodo compound, when it react with initially tertiary butyl lithium and followed by zinc chloride, which produce this corresponding organo zinc compound, which then react with this alkynyl iodide in the presence of palladium catalysis, which readily produce this corresponding carbon-carbon coupling product. So here you should note that the stereochemistry of this methyl group as well as this methyl group as well as the stereochemistry of alkene geometry doesn't affect under this reaction condition. Next, moving on, some more example. This is one of the interesting example. Now you see, so this compound is a dibromo compound which going to react with this organozinc species in the presence of palladium zero catalysis. When you get this type of situation, you always remember in this rule. So this organozinc species always coupled with less hindered side. So now you compare these two sides. So this side is less hindered when you compare to this side. Therefore, this organozinc species coupled with this side to produce this corresponding carbon-carbon coupling product. So next, moving on, some more examples. So this Negishi cross-coupling reaction highly useful for synthesis of intermediates of natural product as well as pharmaceutically active ingredients. So here is one of the example. Now you see this organotriplet compound, so which react with isopropyl magnesium bromide in the presence of zinc chloride initially. So this Crichton reagent react with zinc chloride to produce corresponding organozinc species, which react under palladium catalysis with this organotriplet to produce this corresponding carbon-carbon coupling product. So next, moving on, some more example. So here you see, instead of using organozinc halide, we can use dialkyl zinc also. So in this reaction condition, they used dimethyl zinc in the presence of palladium catalysis or dimethyl zinc in the presence of nickel catalysis, which readily undergo carbon-carbon coupling to produce this product. Here you should note that the fluoro group is doesn't affect under this reaction condition. So next, moving on, some more example. So here you see this is one of the interesting example when you use n-butyl lithium, which readily abstract this bromo group, which produce corresponding lithiated species, which then react with zinc chloride to produce this corresponding organo zinc chloride, which then react with this azyl chloride compound in the presence of palladium catalysis, which readily produce this corresponding carbon-carbon coupling product. Next, moving on, one more interesting example. So now you consider this substrate having two iodo group, one from carbon sp3 and another one from carbon sp2, which going to couple with this organo zinc bromide species under palladium zero catalysis. When you get this type of situation, you always remember this one. So carbon sp2 and carbon sp3 coupling is favored when compared to carbon sp3 and carbon sp3 coupling. So according to this, so this organozinc species which going to couple this carbon to produce this corresponding carbon-carbon coupling product. So this is the another interesting example. So when you take this substrate, when you use n-butyl lithium, which readily abstracts this proton, so therefore this electron shifted here, then followed by a kick of Cl minus to produce corresponding chloro compound species, which then readily abstract that chloro group by n-butyl lithium, which produce corresponding lithiated species, which then react with zinc bromide to produce this corresponding organo zinc bromide species, which then react with iodobenzene in the presence of palladium catalysis to produce this corresponding carbon-carbon coupling product. Up to now, we have seen that Negishi cross-coupling reaction with organohalide with organozinc reagent. So apart from this, Negishi cross-coupling reaction also possible with organoaluminium compounds as well as organozirconium compounds in the presence of either palladium or nickel catalysis. So before moving that, we should know how to prepare organoaluminium compounds or organozirconium compounds. So for organoaluminium, there are the two type of methods to known to prepare this type of compounds. The first one is hydroalumination. So for hydroalumination, when you take the terminal alkyne and react with diol H in the presence of heptane to produce this corresponding alkynyl allenes. So here you should note the stereochemistry of this double bond. So this diol H addition always undergo cis phase, and similarly this aluminum species always take the position of terminal position, while this hydrogen takes the position of inner position of this corresponding alkyne to produce this corresponding alkynyl allane. So this is the another example. So here you see this one is a disubstituted alkyne. When you react with diol H, which produce this corresponding alkynyl allane as a mixture of products. So next moving on, one of the example for Negishi cross coupling reaction with alkynyl allane with organohalide. So here you see this alkyne initially react with diol H to produce this corresponding alkynyl allane, which then react with this corresponding organoido compound in the presence of palladium catalysis to produce this corresponding carbon-carbon coupling product. Here should note that the stereochemistry of double bond here as well as here also doesn't change under this reaction condition. So next moving on, carboalumination reaction. So according to this reaction, when you take the terminal alkyne react with trimethyl aluminum in the presence of zirconium catalysis to produce this corresponding alkynyl allane species. So next moving on, one of the example, when you take this alkyne which react with trimethyl aluminum in the presence of zirconium catalysis to produce this corresponding alkynyl allane, which react with this corresponding organohalide compound in the presence of palladium catalysis to produce this corresponding carbon-carbon coupling product. Next, moving on, organozirconium compounds, how it useful for Negishi cross-coupling reaction. Before moving that, we should know how to prepare the organozirconium compounds. So this is one of the methods for hydrozirconation. So according to this reaction, when you take the terminal alkyne which react with Sievert's reagent, so Sievert's reagent mostly known for the tertiary amide reduction into aldehyde. So here this reagent useful for preparation of organozirconium species. So here you see after this reaction which produce this corresponding alkynyl zirconium. So when you take the disubstituted alkyne, when it react to produce this corresponding mixture of alkynyl zirconium species, but when you take the excess of this corresponding Sievert's reagent, which readily undergo isomerization reaction to produce this alkynyl zirconium as a major product. So this is one of the example when you take this alkyne which react with this Sievert's reagent to produce this corresponding zirconium species. So which then react with this bromo compound in the presence of palladium catalysis to produce this corresponding carbon-carbon coupling product. Here also you should note that the stereochemistry of alkene geometry doesn't change here also. Next, moving on, Negishi cross-coupling reaction by using zinc salt additive. Sometimes when you use organoaluminium or organozirconium derivatives are not sufficiently reactive at the time, when you use the zinc salt that quickly undergo transmetalation reaction with either organoaluminium or organozirconium to produce in situ corresponding organozinc species which then undergo Negishi cross-coupling reaction. So this type of protocol referred as double metal catalysis. So now you see some of the example for that. When you take this disubstituted alkyne, when you react with diol H, which readily produce this corresponding alkynyl allane species, which then react with this iodo compound. So now you note that without zinc chloride additive, this reaction doesn't happen. But in the presence of zinc chloride, this reaction readily undergo to produce this corresponding carbon-carbon coupling product. So this is the another example when you take the disubstituted alkyne, react with Sievert's reagent to produce this corresponding organozirconium compound, so which then react with zinc chloride in the presence of palladium zero catalysis with this organobromide compound to produce this corresponding carbon-carbon coupling product. So next, moving on the Negishi cross-coupling reaction summary. So while the Negishi reaction is highly useful when compared to the Kumada coupling. Since Kumada coupling suffers with a functional group tolerance, so we already discussed about Kumada coupling in our channel. You can find the link of Kumada coupling reaction in our description box. So apart from this, it is important to note that some drawbacks and limitation also associated with the Negishi cross coupling reaction. For example, so propargyl zincs do not couple under this reaction condition, but homopropargyl zinc that can readily undergo this Negishi cross coupling reaction. And apart from this, the secondary and tertiary alkyl zinc may undergo isomerization reaction, but cross coupling with primary alkyl and benzyl zincs also that readily undergo Negishi cross coupling reaction without any issue. And due to the high reactivity of organozinc, that CO insertion usually does not takes place, unlike in the case of less reactive organotins, that is still coupling. And the next point is the need of organozinc reagent, which can be sensitive under open atmosphere and sometimes challenging to prepare. It's a notable consideration. And looking ahead, ongoing research aims to expand the scope of Negishi reaction, innovative in catalyst design and the development of enantioselective version, and even there are a lot of enantioselective version of Negishi cross coupling reaction also known in literature. And further their development continue to push the boundaries of what's possible with this reaction. To sum up, Negishi reacts. Looking ahead, ongoing research aims to expand the scope of Negishi reaction, innovative in catalyst design and development of enantioselective reaction. So even lot of enantioselective Negishi cross coupling reaction also known in literature, and continue to push the boundaries what's the possible with this reaction. To sum up, Negishi cross coupling reaction is a powerful method to form the carbon-carbon bonds. It is versatility, high selectivity, and mild reaction condition make it valuable tool in organic synthesis. By understanding its mechanism and application, we can better appreciate its role of advancing chemistry. That's it for today's lecture. I hope you found this overview of Negishi cross-coupling reaction informative and helpful. So if you have any questions or want to see more examples, just leave a comment below. Don't forget to like, share, and subscribe for more chemistry content. So here are the some of the practice problems. When you get the free time, you just give it a try. And finally, thanks for watching and see you next time.